Hey, howdy folks, it's Virtual Schmied here with you guys today on a video about periodic trends. So you can see the essential question there. Mostly what we are looking for is definitions for atomic radius, electronegativity, ionization energy, and reactivity, as well as the trends for those four things. But before we start on the main four, I want to talk a little bit to make sure we're all on the same page about what is a group A versus a group B element. This becomes really important when we're talking about valence electrons specifically. So the first two columns and the last six columns are our group A elements. These are our group A elements. These are our group A elements. The ones in the middle are our transition metals. Those are our group B elements, and that's all of these. For group B elements, valence electrons are hard to predict. Valence electrons get a little bit messy in the transition metals, so it's hard to predict precisely what's going on there. But for group A elements, the valence electrons are very, very easy to predict. So how do we do that? Well, let's talk definition first. Valence electrons are the electrons on the outermost energy levels. That's the basic definition of it. We'll call them valence electrons, but that's just a fancy way to say those are the ones on the outside. Those are the electrons that are actually available to participate in chemical bonding. The electrons in the inner rings, whether it's just one inner ring or several inner rings, are kind of locked up. The electrons on the outside are the ones that are actually on, well, the outside. They can interact with other electrons on other atoms, but not the ones on the inside. So as an example for valence electrons here, we can look at the Bohr model and see that oxygen has 1, 2, 3, 4, 5, 6 valence electrons for oxygen. You could do the same thing on neon and count 8. But we don't want to draw out a Bohr model for every single element, especially some of the bigger elements. That would be insane to try to draw these Bohr models. So what we can do instead is recognize the pattern for valence electrons. The number of valence electrons is equal to the group A number. So here is group 1A. It's got 1 valence electron. Group 2A has 2 valence electrons. We skip the middle ones because these are our group B elements, hard to predict. And so here is group 3A, and it has 3 valence electrons. Here is group 4A, and it has 4 valence electrons, and so on. This particular periodic table should already be in your notes in periodic layout and coloring part 2. All right, let's get down to the main focus. Let's talk about atomic size and the rest of these trends. So first, a definition. It's half the distance between the nuclei of 2 identical atoms. That's the best definition for it. So in this case, if we had H2, 2 hydrogens bonded together, since they're identical atoms, somewhere in the middle is where one atom stops and the other atom begins. The distance between the center to where that happens is the atomic radius. Really, it's just a question of how big is that atom with its electron cloud included. A lot of times the easier to understand definition is just say the middle of one nucleus to the outermost electron. That doesn't always work for all atoms. Really, the best definition is the first one, but the second one just does just fine. So the trend for that. The atomic radius increases as you go down a group. So as we go down, and as we go left across a period, as we go left. And that's where it increases. So these will be the biggest atoms on the bottom left of the periodic table. And up in the top right, these are the small atoms. I guess I should say smallest and biggest. So the largest radius is actually cesium. Theoretically, it should be francium, but francium is so radioactive it doesn't actually exist for long enough for us to really do any experiments on it and figure out how big it actually is. But theoretically, francium, because it has another energy level, should be bigger than cesium. But for practical purposes, we say the largest atom is cesium. The smallest radius is going to be helium. No exception for that one. Okay, next trend. First, ionization energy or ionization energy. Sometimes we'll abbreviate this as just IE for ionization energy. And it is the energy required to remove an electron. We're ionizing it. We're taking an electron off and removing the most recently added electron from an atom. It's going to take some energy to do that. How much energy is going to depend on the atom. So for this magnesium atom, it's got 12 electrons, and what we're doing is we're taking this electron and ripping it off. We're releasing that electron. How much energy that takes is the ionization energy. Some atoms have a really low ionization energy. They want to get rid of that electron. Some atoms have a really high ionization energy. They don't want to get rid of that electron. And we can tell those trends just by knowing the periodic table. So ionization energy is going to be opposite of atomic radius. Ionization energy increases as we go up and as we go to the right. So the largest ionization energy is going to be in the top right. I'm just going to label this largest IE for ionization energy, and that is going to be helium. Opposite is going to be the smallest IE on the bottom right. And again, that is going to be actually cesium. Theoretically, it should be francium, but we don't have enough francium to actually experiment on and find out. All right, so there is ionization energy. Next trend, and probably the most important trend, I'm going to move my head here so we can see that whole diagram, is electronegativity. And there's going to be a couple of definitions here. The simple definition, how strongly an atom attracts electrons to itself. If something is strongly electronegative, we're going to say it has a high electronegativity, strongly attracts electrons. Or if something does not really attract electrons very strongly, it has a low electronegativity. The more important and better definition is how strongly an atom pulls on bonding electrons. If an atom is pulling on its own electrons, it's fine, it doesn't really matter. But if an atom is pulling on bonded electrons, that's going to greatly determine the type of bond that we will receive, and that's a whole other video and a whole different topic. But let's look at this picture on the right side here. Oxygen has a higher electronegativity, which I'm going to abbreviate EN. Way higher than the two hydrogens over here. Low electronegativity on both of those. So these these electrons in the middle there that are a part of this bonding pair, these are bonding electrons. Those bonding electrons are going to be closer to oxygen because oxygen has a higher electronegativity and tugs on those electrons. It takes them away from hydrogen. It's not that hydrogen's not holding on to them. It's just not holding on to them very tight. It's sharing with oxygen, and oxygen is making sure that that sharing is not very equal. Okay, trend for electronegativity follows ionization energy, which is kind of nice. You don't have to remember both, just one. So it makes sense that electronegativity increases as we go up and to the right again. If those atoms don't want to lose their electrons, that means they're holding onto their electrons very tightly. Electronegativity and ionization energy kind of go hand in hand. They're not the same thing, but they have the same trend. Anyway, up here is going to be our high electronegativity. The largest electronegativity is going to be fluorine. I'll come back to that point. It's a little bit weird. And the smallest is going to be cesium. The reason that the largest electronegativity is fluorine and not helium is because helium doesn't want more electrons. Helium doesn't bond. Oops, whoops. And maybe that's not the most accurate way to say that helium has no electronegativity. It's just that it's defined differently, or rather it's undefined for how much it is electronegative. So the exceptions here are the noble gases that don't have any electronegativity. All right, reactivity is kind of two trends. It's kind of a double one. So the definition for it: how likely an element is to undergo chemical reactions, and when that chemical reaction happens, how much energy is absorbed or released depending on the chemical reaction. So reactivity will help us know, is this chemical reaction going to happen or not? And if it does happen, how much energy is it going to take or how much energy is going to be released? The big exception here is the noble gases over here in group 18 or in group 8A. Those are the same thing. they're almost completely unreactive. So they don't really have a reactivity. They're almost completely unreactive. So let's talk about the reactivity for these. You're going to need to draw quite a bit extra. I'm going to do my best to color code this here. So for metals, different than nonmetals. Metals reactivity increases as we go down and to the left. So this is the high reactivity for metals. And somebody's calling my phone. Oh, it's a scam call. What a surprise. So that is where the high reactivity happens for metals. It's going to be that cesium has the actual highest reactivity of all of them. For nonmetals, the trend is going to be opposite. Let me switch to blue for nonmetals here. For nonmetals, the reactivity increases as you go up and to the right. My writing got a little messy there, but that says high for nonmetals up and to the right. The reactivity of metalloids is really difficult to predict. There's not an easy trend that we can just say up or down, so we're going to leave metalloids alone for now. And the important exception here, even though the noble gases are nonmetals, they're almost completely unreactive. They don't have a reactivity because they don't want any more electrons. They don't want to get rid of any. They don't want to gain any. They're chill how they are. Alrighty, folks, that's going to be it for Virtual Schmied this week. You have just gotten 5 trends, really, because we included valence electrons as a part of that trend. So here at the end of the video, go do your summary, which is just based on the essential question, which is at the beginning of the video and is in your notes as well. So I'm going to go ahead and leave it here. Virtual Schmied,